Section 515.7, Part 2, Triple Integrals in Cylindrical and Spherical Coordinates. Now that we know a little bit about what cylindrical and spherical coordinates is all about and how to convert one coordinates to the next, hopefully, now we are ready to perform triple integrals in cylindrical and spherical coordinates. So this is how triple integral looks like in Cartesian. So this is a function of x, y, z. So you go dz, dy, dx, and 5 other orders. Remember, there are 6 ways to set up triple integrals. When it comes to cylindrical coordinates, the function fx, y, z becomes r theta z. And then the volume element, this guy right here, dv becomes r dz dr d theta. And the volume element for spherical coordinates becomes what? Rho square sine phi d rho d phi d theta. And the integrand is a function of rho and phi and theta. So for spherical coordinates, you go from function of theta and phi to a different function of theta and phi, that's surface to surface. Then you go from curve to curve, so this would be like what? Phi is phi 0 to phi 1, theta goes from theta 1 to theta 0. And here you go from a function of what? Let's say r to a different function of r, and then theta would be constant. So this would be like, let's say, some function of r to a different function of r. Let's say, what should we call this? Let's say we call this w of r, and theta goes from, let's say, 0 to theta 1. Question is, where did these guys come from? R dz dr d theta and rho square sine phi d phi d theta d phi. Well, turns out if you get a piece of cylinder, this is how a typical delta V is going to look like, you know, the volume element. Notice the length of this guy is delta R. The height is delta Z, but this right here, this side right here is the arc length, which is R times delta theta. Remember the arc length, if you have a circle with what? Central angle theta, and this is R, so if you want to find arc length is equal to R times theta from trigonometry, correct? This angle right here is delta theta. This is R, so this arc length is what? R times delta theta, correct? So what happens is the volume would have a dimension of delta R, R delta theta, and delta Z. In other words, think of it as length. Is that right? Length times width times height. So here's the area. Think of it as, you know, we approximate this guy, you know, with a rectangle whose thickness is delta Z. And the width and the length is R delta theta and delta R. So to find the volume, you multiply length by width by height. So this is length, width, height. So lo and behold, if what? If delta Z and delta R and delta theta is small enough, so what happens is delta Z becomes delta dZ, delta R becomes dr, and delta theta becomes what? D theta. And that's basically where the volume element for cylindrical coordinate comes from for triple integrals. For spherical is a little bit tricky because what happens is just like you're cutting the watermelon. First you cut it like, you know, from top to bottom, then you cut it like, you know, from left to right in order to get a slice of the watermelon out of a whole watermelon. So what that means, we need 2 cuts. one from one side of, let's say, from, how would I say this, north to south, and the other one, let's say, from east to west, in order to get a piece of what? Watermelon out of a watermelon or out of a sphere. Okay, so what happens is you have two cuts. Do you see it? Here is one cut, here is the other cut. Okay, this cut right here is the arc length, which happens to be rho times delta phi. This cut, just like, cylindrical, is what? R delta theta. Do you see it? But R in what? Spherical is rho sine phi. So this guy becomes rho sine phi times delta theta. This guy stays as rho, what? Delta phi, not delta theta, but delta phi. And the length here is delta rho. So this is like, the change in the radius of what? Of the sphere. So what happens, just like, previous coordinate system, you pretend this is like a rectangle with a thickness. So the length is rho sine phi delta phi, the width is rho delta phi, and the thickness is delta rho. So you multiply length by width by height, you get rho sine phi delta theta times rho delta phi delta rho, but this gives you rho squared sine phi delta rho delta phi delta theta. That's basically where volume element for spherical coordinates come from. So it comes from this piece of what? Watermelon or what? Or sphere. Okay? So you have to have two cuts, one from top to bottom, one from sideways. So that's what those two cuts are. You see it? So back to our problem. Question is, find the volume of a solid bounded by the surface 9 minus x squared minus y squared, which is upside down what? Paraboloid. So it kind of looks like this. Do you all see it? Okay. And the plane z is equal to 0, y is equal to 0, y is equal to, so these are like coordinate planes. So that means we're in first octant. In cylindrical coordinate system. Okay, so you set up the volume, so that's triple integral 1 dv. So notice dv gets to be replaced by what now? R dz dr d theta. Don't forget there is a factor of r. Okay, so now you go, okay, z goes from the floor to this, which is 9 minus x squared minus y squared, but the projection of this surface on the floor is just 1/4 of a circle. Do you see it, with radius 2? So that's r. This is r right here. So because the projection, the shadow of the sphere is a circle, so it's nice to use what? Cylindrical coordinates. Remember, cylindrical coordinates is three-dimensional version of what? Polar coordinates. So I'm going to rewrite this as 9 minus x squared plus y squared if you factor out a minus. So z goes from 0 to 9 minus r squared, because this guy is r squared. And theta, or I should say r, goes from what? Oh, this is slice of pizza, remember, in polar coordinates, 0 to 2. But theta goes from 0 to pi over 2 and it stops, because we are in the first quadrant of in xy, which is the same as first octant in what? XYZ plane. So now what you do, you kind of what? Integrate this first integral with respect to z. So you get a z here. Evaluate z between 9 minus r squared, you get this. Then you evaluate the second integral as you go from right to left with respect to r. But don't forget to distribute this r factor by 9 minus r squared and then take its antiderivative. So that would be like 9r, but antiderivative of 9r is 9r squared over 2. Antiderivative of r cubed is r to the 4 over 4. R goes from 0 to 2. Evaluate that. You get 14. But now antiderivative of d theta is theta. But theta goes from 0 to pi over 2. So 14 times pi over 2 gives you 7 pi cubic units. And that would be the volume. Do you see it? So notice the question is, when do we use cylindrical coordinates, or what is the application of it? When is it applicable? Well, cylindrical coordinate systems are useful in rotational symmetry kind of solids. Example one would be water flow in a round section of a pipe. Example number two will be heat distribution in a cylindrical metal. Example number three would be electric magnetic field produced by electric current in a long cylindrical wire. So these are the type of or places or applications which it would be nice to use cylindrical coordinates. Do you see it? So everything has to do with cylinder. Do you see it? On the other hand, sometimes we're dealing with spheres, okay, in one form or another. So that's where spherical coordinates kicks in. For instance, let's find the volume of a sphere centered at 0, 0, radius a. Okay, a is a positive real number, correct? You and I, we both know the volume is, this is a well-known solid, as 4/3 pi r cubed, correct? Let me see if I can show you where this formula is coming from. Watch this. So you set up a triple integral dv, but remember dv in spherical coordinates is all of this, which is rho squared sine phi d rho d phi d theta. All of this is dv. And because we're using triple integrals, so the integrand is 1. So now, rho is the radius. So you're going from 0 to what? Till you hit the radius, which is a. So rho goes from 0 to a. Okay. Now, that's from coordinate system to the sphere. Phi, remember, it goes from what? North pole all the way to south pole. Remember, at North Pole, phi is 0. In South Pole, phi is pi, and that's the limitation of pi. Phi cannot, phi cannot exceed pi. So that takes care of what? Phi range. And theta is all the way around because you're dealing with the entire basketball, so it has to go from 0 to 2 pi. Do you see how the limits gets to be set up? So rho is the radius, 0 to a. Phi goes from North Pole to South Pole, but clockwise. At here, phi is 0. Up here, phi is pi over 2. Up here, phi is pi, but that's the limitation of phi. And theta can go 360. So now you got this. So the first thing I did was take the antiderivative with respect to rho. You have a rho square, antiderivative of rho square is rho cubed over 3, 0 to a. Then you have sine of phi d theta. Evaluate this at a and 0, you get a cubed over 3, so that's a constant. You can pull that out. But antiderivative of what? Sine phi d phi is minus cosine what? That would be, let's see now. This is, let's see now. This is supposed to read, sorry guys. This is supposed to read what? Phi, is that right? And phi goes from 0 to pi. So that would be -1 minus 1. But then that's -2 times negative gives you positive 2a cubed over what? 3. But now you have antiderivative of d theta, which is theta. And theta goes from 0 to 2 pi. So that's 2/3 a cubed times 2 pi gives you 4 pi a cube over 3. And that's precisely what the volume of the sphere is. Do you see it? What would be the application of spherical coordinates? Remember, system of latitude and longitude. And that is kind of like divides the Earth surface into a grid for what? For navigational purposes. Remember, I told you spherical coordinates is the fundamental idea behind GPS. That's how GPS finds your destination, remember? Okay, so now let's do a couple of problems here just to make sure we fully understand how this works. Suppose I am asked to evaluate this triple integral. The integrand is xyz, so this is no longer a volume problem, so not a volume problem. Is that right? So I have no idea what xyz stand for. But in order for this to be volume problem, the integrand has to be 1, remember? So, but what is E? E is a solid which is bounded between two spheres. Remember when rho is constant, so these are spheres. In other words, this in Cartesian is x squared plus y squared plus z squared equals 4. This guy in a what? Cartesian is x squared plus y squared plus z squared equals 16. So anytime you have rho is equal to constant, you have spheres. So you have two spheres, same center, and the solid you're trying to find the volume for lies between these two spheres, but it's below the cone. Remember, every time you have phi is equal to constant, okay, this is the equation of a cone, upper half of a cone. So this is like upper half, because remember in the last video we said if this guy is a acute angle, um, you get the upper half. If it is obtuse, you get the lower half. If it's pi over 2, that would be the x and y plane. So notice tan of phi, if you remember, is defined as r over z, but tangent of 60 degrees is what? Square root of 3. So if you cross multiply, you get this. But I can replace the r with the square root of x squared plus y squared. So the equation phi is equal to pi over 4 in Cartesian is z is equal to 1 over square root of 3 times the square root of x squared plus y squared, which is the upper half of the cone. And that's exactly how the cone looks like right over here. Do you all see it? So I'm looking for the solid which is bounded by these two spheres. That's the sphere with radius 4. This is a sphere with radius 2. And this is the what? Cone. So I'm right here. I'm trapped right here. Do you see it? So, how would I do this? Well, first I have to replace the x with what? Its equivalent in what? In spherical coordinates. This is x. This is how x looks like in the spherical coordinates. It's rho sine phi cosine theta. This is how y looks like in the spherical coordinates. Is rho sine phi sine theta. And this is how z looks like in the spherical coordinates, which is rho cosine phi. And the remaining rho square sine phi d rho d phi d theta is dv. Okay? So rho goes from what? 2 to what? 2, 4. This is your rho. This is the limitation of your rho. You have a big rho, you have a small rho, rho 2, rho 1. So you're going from first sphere to the second. Phi goes from North Pole, so this is the North Pole, up to where the cone is. We know the cone finishes at pi over 3, but then this is a solid, so theta has to go 360, so theta goes from 0 to 2 pi. Now, the first thing I did, I multiplied the rows. Notice rho times rho times rho times rho squared is rho what? To the fifth. But antiderivative of rho to the fifth d rho is rho to the 6 over 6, but rho goes from 2 to 4. So I evaluated that, I got this fraction. Next, I have 1, 2, 3 sine phis and 1 cosine phi. So I integrate what? This quantity with respect to phi. So here I said let u be sine phi, du is cosine phi d phi, which I have it right next to it. And don't forget you still have cosine of theta and sine of theta when you do the last integral. Anyways, so this would be u to the 4 over 4, so that's sine to the 4 phi over 4. But remember, phi goes from 0 to pi over 3. Evaluate that, put it on the side, and don't evaluate this. Just for this example, look what you get here. Once again, if I let u to be sine of theta, and du is what? Cosine of theta, d theta. So that would be like what? That would be like sine squared over 2, correct? But the question is, if you evaluate sine squared over 2 at 2 pi and 0, sine of 2 pi is 0, sine of 0 is 0, so it really doesn't matter what's here or what this fraction is equal to, because I'm multiplying the entire expression by 0, so the answer is 0. Obviously, this is not a volume problem, because for volume problem, you can't come up with 0. And on top of it, for volume problem, the integrand had to be equal to 1, not x times y times z. Do you see it? The other example is you have a cylinder which has been inscribed inside a what? Sphere. So do you see it? So the question is, find the volume of a solid bounded by the sphere and the cylinder, which means it lies within both surfaces. In other words, this is what we're talking about. Okay, so we are talking about finding the volume of a solid, which is what? Inside the sphere and inside the cylinder. As if you inserted a PVC, a tube or pipe inside the basketball, but the upper and lower part of the pipe is the basketball itself. In other words, this guy looks like this. One of my students a few years ago, he goes, well, it looks like a pill, like a medicine. And he was right. It looks like a pill. So it says, do it in what? In, let's say, cylindrical coordinate system. Okay. So that's what the instruction of the problem is. So this is a volume, so the integrand has to be 1. Cylindrical dV, the volume element, is r dz dr d theta. Okay, so before we do this, remember z goes from where? From the lower half of sphere to upper half of the sphere, correct? How do I know what's the equation of the lower half and upper half of the sphere? Here's the equation of the sphere, correct? If you solve this for z, you get z is equal to plus or minus the square root of 4 minus x squared minus y squared. Positive belongs to the upper half. Negative belongs to the lower half. So looks to me, I'm going from the bottom of the sphere to the top. However, the intersection of these two surfaces, or the projection of this onto the xy plane, is the circle. Okay, so what happens is, here is the circle, which is what? X squared plus y squared equals 1. Okay, so because the projection is a circular shape, so that's why it was really nice to convert to cylindrical coordinate system, which is what? the three-dimensional version of what? Polar coordinate system. Polar coordinate system does not have dz. It only applies to what? Double integral. So guess what? I'm going to rewrite this as what? Square root of 4, factor out the minus, so you get x squared plus y squared, from these limits. But remember, x squared plus y squared is the same as r squared. So therefore, z goes from minus the square root of 4 minus r squared to square root of 4 minus r squared. And as far as the what? R and theta, you are in a circle, center at the origin, so both of these guys are constant. Radius of this, the length of this piece of pizza goes from 0 to 1, and theta goes all the way 360, which is 0 to 2 pi. We'll never have 360. We always have 2 pi because we're dealing with real numbers, correct? So now, if you evaluate this, you get an answer which is like 4/3 of pi times 8 minus 3 square root of 3. Once again, do not change the answer into decimals, okay? Do not, because the minute you change it into decimal, then you approximate. So on the upcoming test, midterm number 3, we would like, or exam number 3, we would like all the answers in chapter 15 to be expressed in terms of what? In exact form. Exact form. But because you had a perfect symmetry, you could have gone between what? 0 to square root of 4 minus r squared, which is like, find the volume of the upper half, multiply the answer by 2. Or instead of going all the way for theta from 0 to 2 pi, you could have what? Go upper half and what? Quarter over circle, but multiply the answer by what? 8. In other words, this only gives you the volume of 1/8 of the what? Solid. This is like first octant. To find the full volume, you have to multiply by 8. So notice all of these 1, 2, 3 integrals give you the same answer. And that's due to the symmetry. So you can use any of these setups for the limits and yet get the same answer. Thank you.